Hello everyone, my name is Austin, and today I'll be presenting my mini project in digital signal processing, which is audio visualization by means of a real-time spectrum analysis on FPGA. Lower frequencies are at the bottom of the LED strip, while higher frequencies are at the top. In this example, the FFT has been sized such that 3.6 kHz puts the peak of the spectrum at the top of the LED strip. This project aims to give a tool for artists to use in live performances. Live music applications require specialists to create predefined lighting programs for each venue, and most typically this is done right before a show. This forces artists to rely on operator lighting cues, which ultimately limits the improvisational aspect of live performances. So why FPGA? Other microcontroller systems like Arduino and Raspberry Pi have instructional processors. Commands are executed sequentially until the algorithm is complete. While great for multi-purpose use, field-programmable gate arrays allow for reprogramming of the transistor network itself, referred to as the fabric. Here you'll see a functional block diagram describing the hardware inside the FPGA. First, we need a way to visualize the spectrum, and a ws2812 LED driver written in Verilog will allow us to see the spectrum as signal is collected. Next, we need a way to sample the waveform, and a Xilinx ADC block will take care of the heavy lifting for us. Finally, the Zinc processing system, featuring dual-arm Cortex A9s, is implemented to buffer data, perform the Fourier transform, and write colors to the LEDs. So far, the hardware has been described in Verilog, and the AXI peripherals allow for interconnection between the processing core and auxiliary components. So, what's next? Routing data and taking the Fourier transform in C. Here's an overview of the C code loop used to take and display the FFT on an LED strip. First, an ADC sample is collected at the beginning of each loop. When the buffer is not yet full, the stream index is incremented. Otherwise, the buffer is full and the FFT is ready to be taken. A square root function then produces the bin magnitude, and the values are normalized according to the highest stream value recorded. Finally, the FFT values are written to the LED strip, and the cycle is then repeated. A radix 2 decimation in time FFT algorithm is then implemented for an FFT with size up to n equals 1024. The ADC is implemented with a 962 kilosample per second sampling rate and 16 sample averaging. For an FFT with 512 samples, this produces about 60 Hz per LED. Specific application requirements must be carefully considered when implementing this real-time audio device. Decreasing the frequency band for each LED requires increasing the size of the FFT. As this size becomes larger, the computation is too intense for real-time applications. Here you can see the first 50 bins in a frequency spectrum of a sync wave. As frequency increases, the highest intensity LED moves to the end of the strip. When frequency goes back down, the DC component is shown at the beginning of the strip. To use a standard aux jack as a frequency source, two voltage dividers are implemented to scale and bias the input audio wave into a signal readable by the ADC. Thanks.